Semiconducting nanoparticles also, CDS, CDSC, these are nanoparticles, semiconducting nanoparticles. About it, we have to learn optical properties, photofragmentation, Coulomb explosion. Now, the cluster word is used here. Inert gas clusters, molecular cluster. Cluster is nothing but a group. A group of atoms made a cluster, right? So that cluster is nothing but our nanoparticle. So particle comprises group of atom, that is also called as nanocluster. So maybe it is a group of 10 atoms, group of 100 atoms, 75 atoms, like that. So a group of atoms which forms a cluster, the size of that is also in a nanometer regime. Nanometer regime, that's why they are called as nanocluster. Okay, and the properties of these nanoclusters, they are different from the bulk material. Bulk means whose particle size is greater, right, in micrometer, like this. So nanometer size is very small size, of the order of 10 raised to power 9 meter. Nanometer is 10 raised to power minus 9 meter. So very small size particle is there. It is actually a group of atoms, right? And atomic size, you know that it is in the range of 10 raised to power minus 10 meter, right? So Armstrong, it is nanometer. So many atoms form a cluster, and that cluster is called as nanocluster or nanoparticle. In general word, we say nanoparticle, but when we study chemistry or physics, then we use this word nanocluster. Then different types of clusters are there: molecular cluster, superfluid cluster, gas clusters, right? They can be formed by the methods of synthesis. Different methods of synthesis are there: RF plasma method, chemical methods, then thermolysis, pulse laser, right? So all these methods, they are used, different methods. Either there are basically two methods: physical methods and chemical methods. So in physical methods also we are getting nanomaterial. By using chemical methods also we are getting, but the way of reaching the nano size is different. So that forms a method, right? So methods of synthesis are we have to study in this last topic of the unit 1. Now there are further topics: quantum wells, wires and dots. Now the name suggests quantum, that means something very small, right? So quantum wells, wires and dots, these are formed by using various methods. These fabrication of quantum nanostructures we have to study in this topic: quantum wells, wires and dots. So 2D material, nanomaterial, it is also called as quantum well. From these quantum wells we can fabricate quantum wires and also quantum dots. So lithography technique is very useful in formation of these nanostructures. So that method we have to study in this last topic. Then what is the effect of size and dimensionality? That we have to study. Then excitons, single electron tunneling and applications. Their applications as in infrared detectors and quantum dot lasers. We have to study in this topic. And the book is, the single book is here for first 3 units, Owens and Poole, nanoscience, physics of nanosolids. The title of the book is Physics of Nanosolids. So first 3 units are taken from this book, Owens and Poole. It's I will upload the notes on the Google Classroom. You have to join the Google Classroom. I will give you the code. Separate Google Classroom will be there for each paper. Okay. So this is a first unit. Now second unit, vibrational properties, electronic properties and carbon nanostructure. These are the different topics in second unit. So these are optical acoustical modes, vibrational spectroscopy, Raman spectroscopy, IR spectroscopy, surface enhanced Raman spectroscopy. About all these spectroscopies, we have to learn in vibrational properties of nanosolids. Then electronic properties, effect of lattice parameter on electronic structure, free electron model, and then organic solids and semiconducting nanoparticles. That we have to study. All these topics we have to study under electronic properties. Then carbon nanostructures, carbon allotropes, we have to study different carbon clusters, buckyball, C60, structure of buckyball, then larger and smaller buckyballs, carbon nanotubes, its fabrication, structure, electronic properties, vibrational properties, and its functionalization. Okay, and doping of carbon nanotubes, that also we have to study. Then its mechanical properties, then composite and graphene nanostructure, that we have to study. Again, this is taken from Owens and Poole, author of this book. Chapter number 7, 8 and 10. Next is unit 3, mechanical properties and magnetic properties. So mechanical properties says stress strain behavior, then mechanical and dynamical properties of nano-sized devices, nanopendulum, nanospring and all. So small, that means only the introductory part is taken in this chapter. Then magnetism in nanostructures, ferromagnetism, then nanopore containment of magnetic particles, ferrofluids, magnetoresistive materials, ferromagnets, antiferromagnetic nanoparticles, and nanoelectronics. Spintronics is very important part by using magnetism, how it can be used in spintronic devices. So about it we will learn in a small topic, spintronics. Again, it is taken from Owens and Poole. But unit 4 is taken from different book. It is taken from Cadentry and Ozin book. So here in unit 4 we have to study gold nanoparticles, its surface, size, shape, how the atoms are self-assembled on the surface, various defects, then its application regarding in biofield, and then future scope of this gold nanoparticles. Then CDSC, cadmium selenide, all about same topics we have to repeat here. Same aspect we have to study about cadmium selenide, iron oxide and carbon. Okay. So this is taken from one book, single book. So that is Concepts of Nanochemistry, written by Kadimetri and Ozin. Okay. So all these notes I will provide you, so don't worry about it. Now, as we go further, introductory lecture of this nanoscience and nanotechnology, I will explain you, give you glimpses of about nanoscience and nanotechnology. Everybody is familiar with the word nano. Nano means very small, of the order of nanometer, right? But what is exactly this nano size material? What are the effects of size on their properties? Actually, we are learning in our syllabus, right? So just introductory part I am taking today. Myself, Vaishali Raikwar. I am taking this course for the past 2 years, and our lab, nanotechnology lab, is there in our college. So any project if you want to conduct, you are most welcome. And I am also a guide, PhD guide. So anybody, if you want to continue after MSc your PhD, then you can join the lab. Okay. So welcome to the fascinating world of nanoscience and nanotechnology. Now in this presentation, I will explain you difference between nanoscience and nanotechnology. What are these nanomaterials? Why they are important, their classification and properties, and examples, their synthesis methods, their characterization, because only synthesis is not sufficient. Whether the material you prepared is nano sized or not, that is to be tested. Whether you suppose you have prepared aluminum oxide, then it is actually aluminum oxide or any other form of oxide, that is to be tested. So this characterization technique is for that purpose. This one. So different characterization or testing is done once your sample is prepared. We call the material as sample. Okay. Then different testing has done, whether for different application also we need some testing. Those methods are called as characterization techniques. Then we will see in short how to synthesize quantum dots, ZNS and CDS, and different application. Okay. So let us see what is nanoscience. Now, science is the systematic study, you know, of something, right? So if we go deep, and the size of the material you are studying is in the range of 1 to 100 nanometer, then it is called as nanomaterial, and the study of this material is called as nanoscience. So you exact definition is study of the materials at nanoscale and their behavior or response to different conditions. So how the nanomaterial is behaving in a certain condition or certain parameters, they are changed, then what is the effect? Or if you change the size of your material, shape of the material, then what will be the effect of that change on the properties of the material? The study of this is called as nanoscience. Right? So different nanomaterials are there from ancient times also. Our ancestors, they were very familiar with the not only the use of nanomaterials, but the fabrication or synthesis of the material is also was also possible at that time also, right? So different of our Ayurvedic bhasmas and all, these are nothing but nano powders, right? And some colloidal solutions. Some particles are suspended in a liquid. They are called as colloidal solutions. So those solutions were also available. So for medicinal or any other purpose, they use these nanomaterials, right? Now, what is nanotechnology? The application of this nanoscience in various fields of life and in the form of any device is called as application of knowledge of this nanoscience. And nanotechnology is nothing but application of nanosciences, and which is in the form of any device. If you use your knowledge in fabricating any device and use it, then it is called as nanotechnology, right? Technology is related to some application, right? So different materials, you can see these nanobots, and these are blood particles, right? RBCs and all. So these nanobots, they are floating in blood, flow of blood for different purposes, right? So they can be used for drug delivery, medicines. They are taken to a particular cell through blood, right? That is also one work of this nanobots. Nanobots are very useful in medical fields. Then nano solar cells. Now we use this nano word everywhere, right? Wherever the particle size is between 1 to 100 nanometer, we can use this nano word, right? So if solar cell materials, they are having nanostructure, then you can use it as nano solar cells. So flexible nano solar cells are available in the form of thin films. You can apply this film on a substrate and use it as solar cell. So these are nano solar cells, a very newly emerging field of research. This is just animation of carbon nanotubes. Different sizes, diameter carbon nanotubes are there. Buckyballs, fullerenes are there, right? Cage-like structure of carbon 60, C60. So what are nanoparticles? They are nanomaterials. So I have told you the size of the nanomaterial or particle size is between 1 to 100 nanometer. So actually it is the boundary is not specifically mentioned, but the definition uses this word. The particle size is in between 1 to 100 nanometer. For that material, every research worker or scientist use this word 1 to 100 nanometer, then the material is nano material, right? Like this. But actually a specific definition in every book, it is written 1 to 100 nanometer, 1 to 100 nanometer. But above 100 nanometer also, the papers, research paper, research articles, they use this word nano material or nanoparticle. Okay, but this definition uses this word 1 to 100 nanometer. If we go above 100 nanometer, then 101, 102, 200 nanometer, then also some paper uses this, some papers use this word nanomaterial. So it's okay. When we use the definition specifically, then you can write 1 to 100 nanometer. Okay. Now this picture shows you different particles. So different shapes are there, sizes are there, different sizes, right? Spherical or some disc shape, oval shape, right? So all these are nanoparticles. And carbon nanomaterial also, they have different allotropes. Graphene is a very thin sheet of carbon materials bonded with each other. Buckyball or fullerene is a cage-like structure, football-like structure, right? Ball-like structure. And dots, nanodots are very small bundle of this graphene. So different allotropes are there. So what happens to these reduced size particles? They change the electrical, mechanical, magnetic and optical properties. All these properties of material are changed completely. So that is the beauty of these nanomaterials, right? So when we go to nanometer regime, their structure changes from FCC to BCC and all. Various structure changes happens, and that's why their basic properties, electrical properties, sometimes if it is conductor material, then their conductivity increases, right? Like this. Magnetic properties, their magnetism increases and all that. Optical properties, the emission properties will be increased. They will emit more amount of light like this, if light emitting material is there, like this. Okay, so optical properties, all these properties have some changes when the size is reduced. Okay, and it can be observed, it can be proved. Many papers are published on all these properties, and they scientists have shown that when the size is reduced, like this, size is going on reduced, then the properties are they observe different properties at different particle size. Here we will see different property, slight changes here, slight changes here, like this. Okay, it can be advantageous or disadvantageous also. Sometimes for some materials the properties are not enhanced, right? So that in that material reducing the size, reduction of the size causes adverse effect, ulta effect, right? So not always the reduction of size is expected or you can say desired, right? Some materials, they will give you good result in bulk size. Bulk means large size particles, micrometer and all, right? So those material, they are used then in bulk type only, not nano size material. So depending on the material, we can use it according to its properties and what application we are using the material for. Okay. Now for comparison, if you see, this is our earth size, 1.27 into 10 raised to power 7 meter in meter. This is in kilometer, right? And this is football. Football size is 0.22 meter typically. And fullerene, that is carbon 60 material, one of the allotrope of carbon, it is having 0.7 into 10 raised to power minus 9 meter. Diameter is this one. So as compared to diameter of earth, it is very small. It is in 10 raised to power plus 7. It is 10 raised to power minus 9. A vast difference. So you can see 10 million times smaller. This football is 10 million times smaller than the earth. And the fullerene molecule, atom you can say, is 1 billion times smaller than football. Okay, so such is the size difference between Earth and this fullerene material. Okay, 0.7 nanometer. Very small sized material, but it has very good applications. Okay, fullerene's material is very useful material. Now, why are they important? They are important because of their two properties. Relative surface area is very big, increased surface area, and quantum effects. What happens to these nanomaterials? All of the atoms, they are on the surface of the material. Okay, on the surface, when they are there, they are very reactive, highly reactive. So they have greater chemical reactivity. They have greater chemical reactivity. And high surface area. Most of the atoms, they are on the surface only, and that increases in turn it increases its chemical reactivity. Most of them are on the surface, that's why surface energy is also greater, and they shows quantum effects. Okay? So the quantum effects can become much more important in determining the material properties and characteristics, and that leads to novel optical, electrical, and magnetic behavior. So because of this quantum size effects, some new properties other than the bulk material, they come into existence because of this quantum size effects. Their optical, electrical, magnetic behaviors can be changed. They can be tuned. Sometimes this word is used. They can be tuned or tailored. Tuned or tailored. Okay. So that means by controlling the size of nanoparticles, we can tune or tailor the properties of these materials, right? And in turn, we can use it in various applications. Okay, and that is nothing but our research. Research in nanoscience and nanotechnology field always in search of novel optical, electrical, and magnetic behavior. All our materials need some optical properties or electrical properties, right? And or magnetic properties. So according to the type of material, we can use it for different applications, and these applications need some of these properties, right? And it can be then these properties can be tuned or tailored by controlling the size of nanoparticles. Okay, so if you choose a particular field for research, then if you go deeper inside, you can learn many new things, right? Many new, if it is optical material, then you will find new optical properties, right? Like this. So very exciting field of research. Now, for example, this high surface to volume ratio. These materials are having high surface to volume ratio because of the increased surface area. They enables more drugs to be attached to the surface of nanomaterial because their surface area is more, and thus it increases the ability of drug loading. So in medical fields, to for drug delivery, this property can be used: high surface to volume ratio. More amount of drug or that medicine can be loaded, and it can be given to a or it can be sent to a particular location in our body, right? Then it is ease of surface modification, which allows nanomaterial to attach different kinds of conjugate biomolecules. Now, what does it mean? This is a gold nanoparticle, the sphere. Now, on this gold nanoparticle, we can see here minus, plus, and all, right? And some these atoms, green atoms, they are attached, right? So this is called as conjugation of functional groups. Conjugation means attaching, to attach, right? Conjugate, to a conjugate means to attach the surface of this gold nanoparticle some functional material, other groups, functional groups like acetylene group and all, COOH, like this, acetate group. So such kind of organic functional groups can be attached on the surface of different nanoparticles. Here we are using gold nanoparticles, and it can be used for various applications. Okay, according to the your need, or according to the fabrication, we can attach, because of the reactivity of this nanoparticle is more on the surface, we can attach many new materials, new functional groups, and it will form a new material, right? If you use this acetate group, that will be another material. If you use different than the acetate group, other proteins, right? There are so many biological conjugation agents that can be attached to these particles. Okay, and according to the application, you can easily attach them. Okay? That is one of the thing. Then drugs can be protected by nanomaterials to avoid degradation during transport. So we can coat these nanomaterials. Now here conjugation is done on this nanomaterial, but the thin layer of nanomaterials can be also coated on the drugs. Drugs will be inside, on which thin coating will be there of this nanomaterial. Okay, that is also one possibility. It avoids degradation of these drugs during transport from one part of the body. When the drug is sent to other part of the body, then degradation is avoided during transportation by protecting it, by coating it with the nanomaterial, different nanomaterials. Okay, so that is also one possibility. Then nanomaterials can be fluorescent or responsive under UV, visible or near infrared excitation, or electrical field or magnetic field. So this is the optical excitation, and this is electric and magnetic field excitation. So they can be fluorescent by the bombardment of UV light. Under UV light, it will show you some color. They will be fluorescent. Okay, so such kind of fluorescence you can get, yellow, red, and all, right? Here green. So under these various agents, excitation agents, or different fields, the material can be fluorescent. Therefore, the drug delivery can be tracked and the release of drugs by precisely controlled methods. Okay, so various applications, various paths are there, and various methods are there. Okay, now how they are classified? They classification is according to their dimensional properties. Zero dimensional, it consists of spheres and clusters. Spherical, spheres or clusters, these are called as zero dimensional materials. Then one dimensional, which consists of rods, these rods, fibers or tubes or nanowires, wire like structure, they are called as one dimensional. Then two dimensional, films or plates which have length also and breadth also, that is called as two dimensional. And three dimensional, it has three parameters: length, breadth and height, right? So these are cuboid like structures. These materials are called as three-dimensional materials. Then properties of nanomaterials: electrical, optical, that already we have discussed, mechanical, magnetic. How the properties will change by reducing the size, that also one kind of study in about this nanomaterials. Now these are examples. Gold nanoparticles, almost spherical. Not every time it will be spherical. According to the synthesis method, sometimes you will get this hexagonal structure also for this gold nanoparticle. This is Buckminster fullerene, carbon 60 molecule. It has 60 carbon atoms. They are in the form of pentagons and hexagons, right? So very useful material, carbon material. This is nanosphere, iron platinum nanosphere material. Titanium nanoflowers, flower-like structure. All these are materials only. It is taken under different imaging tools, FESEM, TEM or AFM. Okay. In due course of time, you will learn about this. These are the apparatus through which we can take, by which we can take the image of the material in such forms. So you can clearly observe how the atom, how the clusters they are, how the particles they are arranged in the form of nanoflower. This is also nanoflower kind of material, SNO2. These are silver nanocubes, cuboidal shape structure is there. What is the size? 64 nanometer. Okay, so the size of this is 64 nanometer. So such kind of materials, they can be observed with the help of field effect scanning electron microscopy or transmission electron microscopy or atomic force microscopy. As the name suggests, microscope, right? You can see the enlarged image of these particles. And every paper, nanomaterial paper, requires these images, TEM image, SEM image, right? Then only you can claim that your material is nanomaterial. So in IIT, all these facilities are available. They are paid facility. You have to give your material there. They will give you images, right? Then atomic force microscopy is also one of the technique, microscopy technique. Now this is CDSC nanoparticle. cadmium selenide. You can see here the size of this last or first you can say is 2.3 nanometer. Size means you can take diameter, assuming it as spherical nanomaterial. So diameter is 2.3 nanometer, very, very small size. And if you observe it under UV light, what color you can observe? Light blue, right? Bluish. Now here particle size goes on increasing, and in the end you are getting what size? D equal to 5.5 nanometer, right? There is not much difference. At nanoscale 2.3 and 5.5, for us it is almost same, right? But at atomic level they make a large difference. You can see the color is changing, goes on changing if we go on changing the size of the material, right? So larger size material, they are red color, right? And as you go on decreasing the size, it goes towards blue, from red to blue. So which material wavelength is more, blue or red? किसका ज्यादा wavelength है? Yes. Wavelength किसकी ज्यादा है पता है? ब्लू की रेड की?
Red.
Red की, right. Red wavelength is around 600 nanometer, roughly 600 to 700 nanometer, and blue in 400s, right? 427 or something in 400s. So towards left on wavelength scale, blue is on left side and red is on right side. Okay. So as you go on increasing the size, yes, the emission of the light is towards higher wavelength, right? And particle size, if you go on reducing, there is a blue shift. It is called as blue shift. The phenomena is called as blue shift. So as you go on decreasing the size of the nanoparticle, there is a blue shift observed in the material. Okay, so these are called as quantum dots. Very small size, 10 nanometers se bhi kam. When the particle size is very less than 10 nanometer, then they are called as nano dots or quantum dots. Right? So very useful tool we get by changing the size or by tuning the size of the material. That is the gift of nano science and nanotechnology to the world, because just changing the size, you can change the color, emission color, and applications are limitless. Just needs your creativity. Now if you compare the size of the amino acids, different proteins are there, viruses, just for comparison purpose, how their size is in nanometer. Amino acids, glycine is the smallest amino acid. What is the size? 0.42 nanometer, very small. And largest amino acid is having the size 0.467 nanometer. There is not much difference, but at this level, again this matters, this size difference. This is smallest and this is largest, right? For us it is almost same. Okay. Now then nucleotides, other molecules, stearic acid, chlorophyll, you can see 1.1 nanometer. So they are in point only, you can see, right? As you go on, proteins, insulin is one of the protein to 2.2 nanometer. Hemoglobin is having 7 nanometer, albumin 9 nanometer. Then this is having greater. Then different viruses, influenza virus, flu virus, tobacco, mosaic virus, all these are having bigger size. You can see the size 60 nanometer, 120, 140. Okay, just for comparison. So in biology, they deal with more in more nanomaterials in bio research field. Always they use amino acid, protein, and all, right? As far as physics or chemistry is concerned, chemistry is also many times they are using different chemicals, right? And material science is nothing but we have to deal with chemicals only. Okay, materials are made up of chemicals only. So somewhat chemistry is also there in our material science, because synthesis part is always, almost all chemical methods are there, and chemical methods are very easy. They don't require a sophisticated instrument. So at our college level also we can manufacture or we can synthesize many materials. Okay. Now see the methods. Almost 1 hour. Okay, I will finish this PPT and we will stop. Okay. Nanomaterial synthesis process is there. Different. There are two main approaches: top-down approach and bottom-up approach. Now, what is the difference? It is going from top to bottom, and the lower one is going from bottom to top. That means from atomic and molecular level, they are building the nanomaterial, nanoparticles. And here we are taking bulk material, right? And we are crushing it like this and breaking it into smaller particles. So from large to nanoparticles, from very small to nanoparticles, right? Atomic level to nanoparticles. That is the difference. So this is called as physical method. Generally, this method is called as physical method. And from atomic level to nano regime, we generally use chemical method. Different chemicals we are using for preparation of nanoparticles. Now here this is one of the top-down approach, physical method, mechanical milling. Mechanical milling. This is that mechanical milling apparatus in which two steel balls are there, refractory or steel balls. In between these two balls, these materials, they are crushed, right? And by crushing, it is converted into nano material. So this is one of the approach. And in chemical methods, we take some one solution, another solution, they are mixed. Sometimes precipitation is formed. Precipitate is formed. That precipitate is dried and it is converted into powder. That is nano size powder, like this. Okay. So some solution we used. So this sol-gel method is one of the chemical method. Okay. So precursor means, this is precursor means starting materials, right? Our ingredients. In recipe we use ingredient word. Here we use precursor word. Okay. So the starting materials, we the precursors, they are taken. The solution is formed with the help of another solvent, and then that solution, it is either coated by spinning method on some substrate. So thin film is formed. So this is thin film coating, or that solution is allowed to dry clusters are formed. You can see here clusters. These are particles. So after calcination, this powder, nanopowder is made, or this sol is converted into gel by dehydration process, and then that gel is first converted into zero gel, and again it is calcined. Calcined means heated, and then converted into dense ceramic material, or rapid drying of gel will be converted into aerogel, like this. So different forms of the material end products we can get with the help of this sol gel method. According to your application, if you want this as a gel only, then go to this path. Take this path if you want ceramic. Take this path if you want powder, or take this path if you want thin film. So very versatile method, chemical method, sol gel method. Okay. Many materials we can form, we can synthesize with the help of this method. This is another method, chemical vapor deposition. Here vapor of chemical, this is precursor, of which we want particles, nanoparticles. That precursor is vaporized by inductive or resistive heating. Two types of heatings are there. By heating that chemical, vapor of the chemical, it is created first, and then with the help of other reactants, they are converted into cluster form. That means particle formation process, and then it is cooled by condensation process. That cooling process will give you particle, and those particles, they were collected here in this container, right? So different processes are there, heating process, here heating, and here cooling process, right? So a big apparatus is needed for this chemical vapor deposition process. This is co-precipitation, very simple process. One solution is taken, another solution is taken. The solution precursors are such that after reacting these two solutions, some precipitate will form. Okay. For example, here Na2S plus H2O, one solution, zinc acetate plus ethanol, another solution, right? So this solution, by drop by drop, is allowed to mix with this second solution. Then after reaction, white precipitate will form here, and that precipitate will be of zinc oxide, ZNO. So this is precipitation method to synthesize ZNO. So this can be easily done in our lab. This require a big apparatus, big lab, but this can be done in ordinary labs also. It only requires beaker and all, right? And the precursors.
Yes.
So this is very simple method. This is another method, combustion method. Combustion method requires you furnace. Furnace, it can go up to 1000 degrees Celsius. It is in our lab. So these are the pictures of our lab furnace only. So this is formation of aluminum, strontium aluminate. Here metal nitrates are taken. Fuel like urea or glycine is taken. Then it is doped with rare earth nitrates. So rare earths are europium, samarium, then terbium, cerium, and all. So rare earth row is there from that row we can take a required dopant material, and its nitrate is to be taken. So if you want europium to be doped, then europium nitrate is to be taken, and then aluminate is prepared, then sources of aluminum nitrate we have to take. Aluminum nitrate we have to take, and mix all this in a beaker, then keep or transfer that solution into a china clay dish, because this beaker cannot withstand sometimes 1000 degrees Celsius. So china clay material is required, which can go up to 1000 degree Celsius. The temperature they can withstand. Now here the temperature of the furnace is to be keep between 500 to 600 degrees Celsius, and that material will dehydrate first, then auto combustion will take place without any direct heat. We are not supplying heat directly, that means we are not applying it in a flame form. The heat is only in surrounding atmosphere, in which this beaker or china clay ball is kept. So material get combusted here, a flame will be created, and around 1000 degrees Celsius will be the temperature of that flame for a very short span of time. That method is called as combustion method. Okay, on its own the flame is created, and you will get your material like this. You can crush it and form a powder. It is cool to room temperature. So this powder, how to identify whether it is nano powder or not? Again, we have to go for SAME or TAME technique, right? Scanning electron microscopy or transmission electron microscopy. There you can identify your material is nanomaterial or not. Then these are the characterization techniques. First important technique is X-ray diffraction techniques, right? XRD. In short, we call it as XRD. So the graphs we get like this. So these are fingerprints of structure of the particular material. For example, here LaAlO3 material is taken, aluminum LaAlO3, aluminum lanthanum oxide, which is doped with cerium. So this is the graph for that. So the peaks at particular scattering angle, 2 theta is the x-axis, and this is intensity on y-axis. So at a particular angle, these material atoms will scatter the incident X-ray. By using this, we can use this Bragg's diffraction law, n lambda equal to 2d sin theta. We already studied this X-ray, right? So this Bragg's law, according to the Bragg's law, we can get the diffracted peaks at a particular angle, right? And this is match with the standard one, whether your material is formed or not, how to identify whether it is synthesized properly or not, by matching these two patterns. This is standard graph, and this is the graph of your material sample, right? And by matching the peaks, you can confirm the formation of a particular material. This is one of the technique. Then second technique is field emission electron microscopy. I have told you already. This is that machine, FESM machine, where electron beams are used. Accelerated electrons in the form of beam, they are used for image formation. Okay, they are bombarded on the sample. Secondary electrons are ejected. Detector catches these electrons and produces electrical signal accordingly, and that is converted into image. So how much they are getting the secondary electrons are ejected. According to that, the surface depth is given, right? Accordingly, the image is formed. So you will get the surface structure or surface morphology of your material by using this FESEM technique. The resolution is 1 nanometer, so nanometer size material also can be easily seen with the help of this FESEM technique. How much voltage is needed? 0.5 volt to 30 kilovolt. So we can accelerate electron with this voltage. Okay, according to the setting, you can set the voltage, you can accelerate the electron according to the need. What type of material is that under test? According to that, the technician sets this accelerating voltage. Okay, I hope I'm making the points clear. If you have any doubt, you can ask in between. This is actual images. During my PhD, I have taken these images, FESEM. You can see clearly morphology. This is spherical and these are tube-like structure, right? And the software attached in that computer attached to that apparatus, it has software which can draw actually the size they can mark on the image. So 20.7 nanometer, 18.5 nanometer, 17.6 nanometer is the diameter of these tubes. You can see here also size of the particle, right? 24 point, 26 point, 26 point. So very good. Nowadays apparatus are available for research. Earlier it was not the case. This is SR2 SiO4, lower one. Which is doped with Eu3+. So these material, strontium silicate, doped with europium. These are light emitting materials. Okay. So if you change the size of these tubes, maybe the color can be changed. Okay. So we can take different methods, slightly change the parameter during synthesis, right? And the size will be changed. Size will be changed, then the properties will be changed. So such will be the procedure for tailoring the properties of material, nanomaterials. Okay. Next is TEM, transmission electron microscopy. This is Philips CM200 TEM machine, which is available at IIT. Again here accelerated electrons are there, which are accelerated with the voltage 200 kilovolt. It is a very big voltage, kilovolt, 10 to the power 3 volts. They are focused by electronic lenses. So here lenses are there. It's objective lens, right? Diffraction lens. So these lenses are there to focus the beam. Then now why this is called as transmission electron microscopy? Because the electrons are transmitted through your thin specimen, thin sample. In earlier case, in FESEM, the electron beam is not transmitted, right? It just bombards the surface. So it cannot pass through the sample because what is the voltage here? Accelerating voltage only 30 kilovolt. And what is the voltage here? 200 kilovolt. So due to this high voltage in TEM machine, the electrons can transmit through the thin specimen. Your powder specimen is suspended in a liquid, generally ethylene, and then the drop of that is then mounted on a carbon grid. A very thin layer of your material is formed, and then that sample is then kept here. This is the sample holder. If you can see here, black color, you can take out this tube, keep your sample thin film, very thin film of your sample, and then keep this tube back in this sample holder, right? And then electrons are allowed to pass through this sample, and here you can see the image of your particles, right? This is that screen, computer screen. I hope it is visible. This is computer screen on which we can see our image, we can store it, and then you can take it. The technician generally emails us. We cannot use our pen drive there because of the virus problem. So they mail us the images, right? This is that section, this one. This interaction of electrons occurred there with the specimen, and the image is formed, which is magnified and focused on imaging device. From this microscope, we can see here also, right? This is the working of this TEM. A large maintenance, a great amount of money is spent in maintaining this device. It requires AC all the time, 24 hours.
Yes.
Huh? Yes. Have you seen this machine? Anybody?
Yes, ma'am.
कहाँ पे देखे?
I am visiting in pharma industry.
हाँ
There I also saw
फार्मा
at
इंडस्ट्री.
Dombivli.
ओके.
हाँ.
वहाँ क्या करते हैं आप?
I also, मैम, SY में जो हमारे कॉलेज की विजिट हुई थी, वहाँ पे हमें फार्मा इंडस्ट्री में ये मशीन्स दिखाए गए थे. सो उसको मेंटेन करने के लिए मैम एसी में इसको केप करके रखते हैं. इसका कॉस्ट भी बहुत सारा, मतलब मेंटेनेंस का भी.
Right. So for college, it is not possible to purchase actually.
Yes, yes,
लाखों
ma'am.
करोड़ों में इसका कॉस्ट रहता है, and to maintain it is also costly. तो IIT वगैरह जहाँ पे रिसर्च होता रहता है, so that they can afford. They have big projects under which big funding also from government. So under that they purchase this apparatus by just paying rupees almost कितना था 1275 per sample. एक सैंपल का वो आउटसाइडर से इतना लेते हैं 1275 प्लस टैक्सेस होगा, राइट? सो आप अगर आपका एक सैंपल उनको देंगे आफ्टर one month according to the slot availability of the slot, they will give you one date. At that date you can go there, sit with the technician and see your sample, how what images we want, they can give you. आप बोलना है उनको कि ये इमेज कैप्चर करो, ये इमेज कैप्चर करो, then they take that image, this save it and then mail it. ऐसा प्रोसीजर है. So nevertheless we are only dealing with the imaging only, right? हमें images चाहिए. Then we analyze that image and write the analysis in our research paper. That is our work, right? So how it is done and which machine, but we have to mention this IIT name in the acknowledgement and the machine model number and all. That is necessary for research article. रिसर्च पेपर जब हम पब्लिश करते हैं तो ये उसमें जरूरी होता है. Okay, which device you have used for imaging or for testing, that is necessary. So we also take our students to for visit to IIGM and all. There also we Panvel में है Institute of Geomagnetism. There also we can see some of the machine. TEM तो नहीं है वहाँ, but other machines we can see which are related to geomagnetism. बट ये भी काफी है कि हमें ये मिल जाता है ना, आउटसाइडर को वो देते हैं एक्सेस, उतना भी काफी है, अदरवाइज रिसर्च नहीं हो पाएगा फिर. ओके, टीएम इमेजेस का ऐसा दिखता है, ब्लैक एंड व्हाइट इमेजेस. अगेन दीज आर फ्रॉम माय पीएचडी रिसर्च. दीज आर लैंथेनम एल्यूमिनेट, दीज आर lead calcium diborate doped with europium. So you can see here particle size. जो यहाँ पे स्केल दी रहती है that is 100 nanometer. यहाँ लिखा है 100 nanometer, right? So if particle is this size, then it is 100 nanometer. तो यहाँ पे भी मार्किंग किया है, वो दिख नहीं रहा है यहाँ, बट ये स्केल जरूरी होता है. जैसे हम ग्राफ में लिखते हैं ना 1 सेंटीमीटर इक्वल टू सच एंड सच, राइट, एक्स एक्सिस वाई एक्सिस, वैसे ही ये स्केल जरूरी होता है जिससे पता चले कि ये कितना साइज का पार्टिकल है. ऑलमोस्ट वी कैन नॉट एग्जैक्टली राइट, राइट, और पार्टिकल्स दे आर ऑफ स्लाइटली डिफरेंट साइजेस आल्सो. एकदम ही यूनिफॉर्म हर बार होंगे ऐसा नहीं है. ओके, दे कैन बी, बट डिफरेंट साइजेस भी हो सकते हैं. This is another technique called as SAED, selected area diffraction, electron diffraction, SAED. Okay, जिससे आपको planes, lattice planes पता चलते हैं. So structure we can identify whether this is FCC or DCC or simple cubic. Okay, तो ये भी एक TEM मशीन में फैसिलिटी होती है. This is another machine called as nanoparticle tracking analyzer, NTA. Here we get distribution, size distribution of nanoparticles. It uses a Stokes-Einstein equation, dt equal to, dt is the particle size, 2tk divided by 3 pi eta rh. So here laser light is used, it is scattered, and there is CCD camera, charge coupled device camera, which tracks and records the Brownian motion of individual particles. Because of this light, the particles get scattered and they will move. So the Brownian motion of individual particle in the suspension, that is tracked, and according to this equation, Stokes-Einstein equation, this particle size is directly proportional to, that means is proportional to the distance covered. The movement of the particle is related to a particle size according to this Stokes-Einstein equation. And then this R is that Brownian motion, that means the distance traveled by the particle. So at a time, simultaneously, this CCD camera is tracking the particles movement, and simultaneously it will give you the size distribution. So on x-axis there is particle size, this one, and count, that is number of particles, they are on the y-axis. So this is called as particle size distribution. If number of particles having this much size, for example 5 nanometer is this one, that is 10 particles are of 5 nanometer, like this. So this is called as particle size distribution. So this method is called as dynamic light scattering method. Right? So this is also very good apparatus for nano materials. size distribution, generally used for biological materials. These are applications in day-to-day life you are familiar with. In every sector of life, they are used: IT, energy, medicine, consumer goods. Okay. So as they show different properties than the bulk, so their applications are limitless. Many opportunities, research opportunities are available in nanotechnology and nanoscience. But there are disadvantages also. Because of their high energy, they are unstable. So instability is the first disadvantage. Some materials, they turn toxic. Some nanomaterial at nano size level, they turn toxic. That is also not all, some. Some may cause explosion when they form oxide, because atmospheric oxygen immediately react with the nanoparticle and they form oxide. And some may cause explosion. Then they agglomerate immediately because they have tendency of reactivity. They have highly reactive. That's why they react with each other and they tend to agglomerate. They come together and form larger cluster, and that will change their property again. Size changes, property changes. So for what property you are designed or for you manufacture, that will then goes in man, right? The property will change, no? So agglomeration is also one of the disadvantage, but that can be overcome by forming a layer on these nanoparticles so that they cannot agglomerate with each other and they will not form that cluster, bigger cluster. So that is called a surface passivation to form a coating. It is just like if we form oily layer on particles, they will not come closer with each other. They will tend to remain away from each other like this. Just a separation layer between two particles. So all these disadvantages can be taken care by one or many methods like passivation method. Now they are hard to control. They are hard to control size and shape of nanoparticles. That means it is very hard to control size and shape of nanoparticle. But we can tune and tailor also, right? In some method, controlling the size and shape of nanoparticles is difficult. But then proper choice of method and materials, that is one of the solution to control the size. The proper method you can choose for preparation. Now quantum dots based drug delivery system to target cancer is one of the example. So quantum dots are tiny particles like CDSC or ZNS, which range from 2 to 10 nanometers. So below 10 nanometers, they are called as quantum dots. So if I am able to fabricate carbon nanomaterials, which are having particle size between 2 to 10 nanometers or 1 to 10 nanometers, below 10 nanometers, then they are called as carbon nanodots like this, right? These are quantum nanodots, quantum dots. So quantum dots can be assigned, they can be conjugated to different antibodies or peptides which are specific against the cancer marker on the surface of target cancer cells. So generally these are used for cancer treatment to identify that cancer cell and to provide the particular drug to that cancer cell only. So that will avoid destruction of healthy cells also, right? So you know that the adverse effect or side effect of cancer drugs are that they destroy the healthy cells also. Around healthy cells are there. Affected tumor part has some healthy cells also, that those cells are also destroyed during the treatment. So they can be avoided by using proper quantum dot size, very small size nanodots. They can be used for conjugation purpose, right? And the treatment can be, you can say, it will avoid the destruction. These are ZNS nanoparticle, very good picture you can see, colorful, right? Various shapes and sizes are there. This is flower shape. All these are tube-like structure, spongy nature, right? Various shapes and sizes are there. Now here, nanobot attacking the cancer cells. Very good animation. Okay, synthesis part I will skip. Now this picture also we have seen earlier. A larger size nanocrystals, they are red color. A smaller size blue color. So blue shift is there. So 6 different quantum dot solutions are shown excited with a long wave, that is 368 nanometer UV lamp. So if UV light of 368 nanometer is allowed to fall on these nanoparticles having different shapes, they will give you different colors. Now these are the MSc opportunities for nanoscience and nanotechnology courses are available in different institutions in India. Now you are in MSc, so I will show you the research opportunities institutions. So these are various labs, institutions and universities. So in various universities nowadays, this Center for Nanoscience and Nanotechnology, they are available. So in our Mumbai University also, there is a center where SEM, XRD and all these facilities are available. Their MSc is also in nanoscience and nanotechnology, not in physics. So interdisciplinary students can join that. Means chemistry students can also join MSc in nanoscience and nanotechnology, physics also, bio also. All they can join MSc nanoscience and nanotechnology. After that, then go to research to these labs. National labs are there: DST, DRDO, CSIR, ISRO, UGC, and institutions are there: Institute of Science, Bangalore, NITs are there, IITs, ICERs, and different universities. Almost all universities nowadays are having this section, Center for Nanoscience and Nanotechnology. Now, industries and companies who hire these professionals are this one: various industries, almost all industries, including food, right? So very good field. So I will end here. If you have knowledge, give it out. Okay. If you have an idea, perform it. And you have a goal, achieve it. That's all. And last, who is this? Can anybody identify? Who is this scientist? किसने बोला ऐसा? Still there is a plenty of room at the bottom. Whose quote is this? नानो साइंस के जनक रिचर्ड फेनमैन. Okay. Still there is a plenty of room at the bottom. Bottom means at the lower level. Lower level means in the nanometer, at the atomic and molecular level. So still there is a plenty of room. Means a vast field of research is open in nanoscience, right? That is the meaning of this sentence. Thank you. Now I will post this